Secondary and tertiary alcohols can undergo SN1 reactions if we treat them with a strong hydrohalic acid. So that's HX. And so the strong hydrohalic acids that you can see undergoing these reactions would be HCl, HBr, or HI. Hydrofluoric acid is a weak acid and will not undergo this reaction. So it's desirable to do a reaction like this in order to convert a secondary or tertiary alcohol into an alkyl halide. So alkyl halides have much better leaving groups, and then that gives us access to substitution and elimination reactions we want to further functionalize. So looking at this reaction mechanism, so I'm showing a tertiary alcohol reacting with HX, and again, X could be chlorine, bromine, or iodine. And so the first thing that takes place in this reaction is the acid-base reaction between the oxygen and your acidic hydrogen. So the alcohol acts as a base and it grabs that acidic hydrogen, and then the bond between the hydrogen and the halogen is broken. And so after this happens, what we have is a protonated alcohol. And so by protonating this alcohol, we took a poor leaving group, hydroxide, because that would be a strong base, and we converted this into a good leaving group, because once this leaves, it will be a neutral water molecule. And so if we're looking at a secondary or a tertiary alcohol, the reaction pathway is SN1. So that means that after we form this good leaving group, it leaves. And so it leaves to give a carbocation. And so we have this flat carbocation intermediate. And this is really reactive. We've formed a nucleophile in this step because we formed X minus. And so what happens next is that X minus will come and form a bond with that carbocation. So overall, we have taken an alcohol and we have made an alkyl halide. Which again, the alkyl halide has a much better leaving group, and it can undergo a variety of substitution and elimination reactions. Okay. This is a reaction with a tertiary alcohol. So when you react a tertiary alcohol, you typically end up with the most stable carbocation that you can form from that first step, because it's going to form in a tertiary center. If you do this reaction with a secondary alcohol, so let's draw a secondary alcohol. If we do the reaction with a secondary alcohol, I'm going to make it a chiral alcohol. So if we do this with secondary alcohol, we need to watch out for carbocation rearrangements. Because it's a secondary alcohol, the first carbocation you're going to get is also going to be secondary. So let's take a look at this reaction. The first step is going to be the same. Right? Your alcohol with its lone pairs of electrons is going to act as a base and attack that acidic hydrogen, breaking the bond between the hydrogen and the halogen. And so we get this protonated alcohol as an intermediate. And the protonated alcohol is, again, a really good leaving group. And so it's going to do what good leaving groups do, and it's going to leave. And this gives us a carbocation. In this case, we have a secondary carbocation. And so we really need to watch this closely and see, can this rearrange to become more stable? Because if it can, that rearrangement will take place quickly, and it will take place before the halide nucleophile can react. And so if we look at this secondary carbocation, we see we've got this quaternary center next door. So one of these methyl groups can shift, right? And so that'll quench the positive charge on this carbon atom, but we're taking electrons away from the adjacent carbon atom. So that's how the positive charge moves, right? So we still have one methyl group on this carbon. We've moved one over, so there it is. And the positive charge is on this carbon atom. Okay. If you're having trouble seeing where the positive charges are, it might help you to write in the implied hydrogens. We do have a hydrogen on this center, right? It had 4 bonds. And so here, the third bond was to hydrogen, and after you move the methyl group, it has 4 bonds, and that's how it's neutral. Okay. And so after we've moved that now we've got a stable carbocation. It's not going to rearrange it further, and the nucleophile that halide ion can attack. So forming a new bond, and we will end up with this alkyl halide. So a couple things to note with these SN1 reactions. Because you have a carbocation intermediate, whenever you have a carbocation, you have to watch out for a few things. And so one of the things you need to look out for is rearrangements. Carbocations are tricky like this. They'll move around if they can become more stable. So we're going to say we're going to watch for rearrangements. And the other thing that we need to consider with carbocations is stereochemistry. So neither one of these examples gave us a chiral center. This one started with a chiral center, but we didn't end with one. But if you do form a chiral center, you will form a racemic mixture, and that's because the carbocation is flat, and your nucleophile could attack it from either side, which would give you a mixture of stereoisomers. So if a chiral center is formed in the reaction, you will have a mixture of stereoisomers.